Okay, Jai Hind. Good evening to all. Today we are going to discuss with the Thevenin's theorem, how we apply the Thevenin's theorem to different problem of the electrical and electronic circuit. Okay, so let's start with the statement of Thevenin theorem. So Thevenin theorem states that any complicated network across its load terminal can be substituted by a voltage source with one resistance in series. Means if we are having a complicated complex network that have a voltage source and some resistance, some other elements, then generally we are going to take that if a load is there, we consider a load resistance. Okay, so then we convert the this complex network into a simple two-terminal network that consists of a voltage source and equivalent resistance of that particular network. Like here we can see that any network, any complex network we are having, like this voltage is V1, there is a resistance R1, let it resistance R2, here it is R3, it is R4, and here it is R5, and here we are connecting the load resistance. Okay, so this network, this internal network, that can be converted like this one: equivalent voltage source in series with the equivalent resistance, and here it is load resistance RL. So this type of theorem can be used if we are having a same source and we are changing the load resistance, we are changing the load, source is same. Then if we find the Thevenin equivalent circuit, then it's easy to change the load and calculate the current, what is the value of current and what are the voltage across that variable load. So that is helpful. And this theorem helps in a study of the variation of current in a particular load branch when the resistance of the branch is varied, that we have discussed, while the remaining network remains same. If remaining source network are same, then we can vary the load resistance, and with the help of this Thevenin theorem, we can easily calculate the current in that various load resistance. A more general statement of Thevenin's theorem is that any linear active network that consists of independent or dependent sources. Independent voltage source means that are fixed. Their values are not going to change with the time, or they are not dependent on the other system. And dependent means they are dependent on the other parameters of the network. That is the main thing. Independence means they are fixed. They are not dependent on the other parameters of the branch of the circuit. But independent source, they are dependent on the some other values, okay, by an equivalent circuit. So we can replace that network, and it can be replaced by having a equivalent voltage source, that is also known as a Thevenin voltage, okay, and in series with the equivalent resistance, that is this one. R equivalent, we can say that R equivalent or RTH, both are same, okay. And where the voltage source being open circuited, and what are the equivalent voltage source? What is the equivalent voltage source? So equivalent voltage source, that is open circuit voltage across that particular load terminal, okay, in which the current is to be asked to calculate. So that load terminal, the voltage, open circuit voltage across that load terminal, and what is the resistance, equivalent resistance? So this resistance that is calculated across that particular load terminal, okay. And there it is well said that it is open circuit voltage between the required two terminal called the Thevenin voltage, and RTH is the equivalent resistance of the network as seen from the two terminal, that is load terminal, with all other sources replaced by their internal resistances. That is very important. Here it is said that P if we are having a voltage source in the circuit and we are going to calculate the Thevenin resistance, or we can say that equivalent resistance, then first of all we have to deactivate all the independent sources. Here the word independent sources only. We can deactivate independent source only, not the dependent sources. Okay. Deactivation means the voltage source or current source, they are replaced by their internal resistances. Means here if it is a voltage source, independent voltage source, so in this case they are replaced by a short circuit. In case of voltage source, we have to replace the voltage source by short circuit, and in case of current source, this can be replaced by open circuit. Okay. Then we are going to calculate the equivalent resistance across that particular load terminal. So that is the main thing. Okay. So now we have to calculate two things. One is open circuit voltage VOC, and second is RTH, or you can say that R equivalent. First one is this one and second one is this one. Okay. So let's start. So this is the explanation of Thevenin's theorem. We are having a network that consists of voltage source Vs, here is resistance R1, R3, R2, and here it is load resistance RL, that is varying. Okay. Then, so first of all we have to find out the VOC and RTH. So let us consider a simple DC circuit as shown in figure above, where we have to find the load current IL by the Thevenin's theorem. So we have to find out the current in the RL branch. Okay, RL, that is your load resistance. Okay, and in order to find the equivalent voltage source, or we can say that open circuit voltage source, or we can say that Thevenin voltage. Okay, all are same, and RL is removed. So first of all, we have to remove this RL from the network. Let's see terminal AB. Okay. So our first step is to remove the load resistance from the network. Okay. So first of all, we remove the RL, okay, from the circuit, and then we are going to calculate the VOC and RTH. Okay. So let's see, the network is here. So after removing the RL, our network becomes this one. This is open circuit. This is open circuit. Okay. Open circuit means here the current, the value of current is 0. Okay. So in this resistance R2, the value of current is 0. Okay. So means the voltage across this terminal AB, that is equal to the voltage across terminal, you can see D. Okay. So VAB, that is equal to your VCD. Why? Because the current is 0 in branch R2. It means the voltage drop is equal to 0. There is no value, that is 0. It is redundant. This branch is redundant. There is no current is flowing in this particular resistance R2. Then here it is VAB, that we can say that is VOC. Okay? VOC, that is VAB, that is VCD. What is the value of VCD? We can have voltage divider rule. The total voltage that is given Vs, and it is across the combined of R1 and R3. So what is the value of VCD? That becomes Vs into R3 divided by total resistance R1 plus R3. We get the value of VOC. Okay. So this is your first part. We have calculated the open circuit voltage, or we can say that this is your Thevenin voltage. This is also called Thevenin voltage, VTH. Okay. By removing the load resistance. Okay. Now, to find the internal resistance of the network, Thevenin's resistance, or we can say that equivalent resistance in series with the open circuit voltage VOC, also known as Thevenin's voltage VTH, the voltage source is removed, or we can say it is deactivated by a short circuit. As we have discussed that the in case of calculation of RTH, we have to deactivate all the sources that are available in the circuit, and that source must be a independent sources. If we are having independent and dependent, then we talk later about that in this lecture. So here we have short circuited this is your short circuit. Short circuited the voltage source. So after short circuiting, the voltage across that particular branch becomes 0. So if we have to deactivate the voltage source, then it means that we have to short circuit that particular branch. Okay. So here it is RTH. So we have to calculate the resistance, equivalent resistance from this terminal to this one, from load terminal to the source terminal. We are moving towards from load to source, not from here to there. It's from AB to this source part. So here we can say that, so this one R1 and R3 both are in parallel. As we can see that current division takes place, these two resistances are in parallel, and this one resistance in series with the total equivalent of R1 and R3. So what is the value of RTH? This R2 plus the equivalent of this R1 parallel R3. So what is the equivalent? R1 R3 divided by R1 plus R3. Okay. So this is your total equivalent resistance. Okay. Now it is this one is called equivalent Thevenin circuit. This one. So here it is the VTH and RTH, both are in series, and here is terminal AB. Again, what we have removed, we have to just reconnect here. Okay. So the value of current, that is, you can say that this one is IL. So IL is VTH upon RTH plus RL, because RTH and RL, they are in series. So total resistance is RTH plus RL, and total voltage is VTH. Then what is the value of current? That is VTH upon RTH plus RL. So if we are continuously changing the value of RL, so we can have this formula. Okay, these are fixed values, and we change the value of RL, we will get the different current with different load resistances. That is the advantage of Thevenin theorem. Okay. And the same thing, VTH is the Thevenin voltage, and Thevenin equivalent voltage, it is an open circuit voltage across the terminal AB known as load terminal. RTS, that is the equivalent resistance as seen from the load terminals, where all the sources are replaced by their internal impedances. Impedance, if we say impedance, then it becomes common in general, that is for AC and as well as for DC circuit. Okay, so here it is. Some steps are given that we have somewhat discussed. First, we have to remove the load resistance, then replace all the sources by internal resistance. If source are ideal, then short circuit voltage source and open circuit the current source. Now find the equivalent resistance, then find the equivalent voltage source. Here the method, that is the very important point, is that here we have to find out the VOC is same. VOC, the process of calculation of VOC, that is same for if the circuit consists of a dependent or independent. In both cases, the procedure is same. But the method of finding the Thevenin resistance, if the circuit consists of a dependent source along with the independent source, they are different. Okay. So first we have discussed already, for independent sources, the most common method of finding equivalent resistance or internal impedance of any linear bilateral network containing independent current or voltage source only is to deactivate the source by its internal resistance. So that is only for independent sources. Okay, this is only for independent sources. Only independent sources are there. Okay, so that we do, and we did that. And for independent current source, as we have discussed that in case of independent current source, it is going to be open circuited. Current source open circuited, voltage source short circuited. Okay, so it is deactivated by the similar thing. Okay, that is the important thing. That is the for dependent sources. If there are some dependent sources along with the independent sources, then how we find the RTH in this case? So there are two methods to find the RTH in this regard. So first method here is the first of all find open circuit voltage across the load terminal by conventional method, either by mesh or node analysis. Now short circuit the load terminals and find the short circuit current ISC through the shorted terminals. So here if we are having let's have some network V1, R1, R2. Here it is, let's some have a dependent sources. Let's it a current I1, 3I1. This is the symbol of dependent source. Diamond shape, plus minus. This is dependent voltage source, dependent current source. Okay. This one is dependent voltage source, that is current source. And let's having resistance R3. Here it is load resistance RL. Okay. So in this case, first we have to open circuit this load terminal AB. First is to open the AB terminal and find the VOC voltage. Second is short circuit the AB and find ISC. By conventional methods, you can use mesh analysis, nodal analysis, whatever you want to. Then the value of RTH become VOC upon ISC. Okay. So this VOC actually your VTH. Okay. So in addition, because you have to already calculated the VOC, Thevenin voltage, you have to calculate, that is same procedure. So this one is calculated. In addition to this one, you have to only calculate ISC in this case. Okay. So you have to short circuit that particular load terminal and find out the ISC. Okay. So then you can get the value of RTH, that is the ratio of open circuit voltage across that particular load terminal divided by the short circuit current that is derived from that particular load terminal. We have short circuited that load terminal and then, okay. The second method, this one that we have described, that how we find VOC and ISC. Here the second method is, whatever the load terminal is there, we have to put a voltage source VDC. Here it is terminal AB and that injecting current IDC. Here it is your RL AB. This particular terminal that is replaced by this one VDC, that is injecting current IDC into the network. Okay. So here it is RTH. So as the one more method to find the internal impedance is firstly the remove the load resistance. We have removed that particular load resistance RL and apply a DC driving voltage VDC at the open circuit load terminals. Keep the other independent sources deactivated and keep other independent sources deactivated. Okay. When a direct current is applied to the load terminal. So in this case, we have to, in addition to this one, and also deactivate all the independent sources. Okay, and keep the dependent source as it is. There is no change with the dependent sources. Okay, when the voltage is applied by the DC supply to the load terminal, a DC driving current IDC, okay, start flowing in the circuit of the load terminals. This is because of application of VDC. When we apply the voltage source VDC, there is start IDC current that is flowing in the circuit. So internal impedance of the source network is obtained by the equation given below, that is ratio of VDC upon IDC. So when we apply the KVL and KCL, whatever the mesh analysis, node analysis, we will get a relation between VDC and IDC, because this is unknown quantity. VDC and IDC is unknown quantity. But when we are going to apply the mesh analysis and load analysis, we will get the some relations, and we will get the ratio VDC upon IDC, or the ratio IDC upon VDC. So from where we can calculate the value of RTH. So there are two methods to find the equivalent resistance in case of dependent sources. In case of only independent sources, that is your conventional method, deactivate all the sources and find out the equivalent resistance across that particular load terminal. But if the network consists of dependent sources, that is, you have to be care and check where dependent sources are there or not. Okay. So thus just keep in mind that if a dependent source are there, the symbol that I have told you, what are the symbol of dependent sources? If dependent sources are there, then be careful for the calculation of RTH and RTH only. Okay, because VOC are same. So here we are having some example. Find the Thevenin equivalent circuit for the network in the shaded area of the network figure. Then find the current through the RL of the values. RL here, the value of RL have two values, that is 2 ohm and 10 ohm. So firstly, we have to find out the equivalent Thevenin circuit of this particular circuit. Okay. So here it is terminal AB. Okay. Voltage given, that is 9 volt, 3, 6. Okay. Let's see. Here the step 1, we have removed the load resistance. RL we have removed. Now we have to calculate VOC plus minus. Here we can see that is very easy. There is no resistance are there in this. So here it is VOC. The VOC that is equal to, you can CD. Okay, that is VAB. That is VCD. Okay. So the voltage divider rule, the voltage, total voltage 9 volt, and that is across 3 plus 6. What is the 9 into 6 divided by 9, that comes 6 volt. So we have calculated the value of VOC simply, or you can apply you can calculate the current, because here the current value of 0. So you can calculate the current I equal to 9 upon 9, that is 1 ampere. And what is the value of V6 ohm? You can say that I into 6. What is I? That is 1 into 6, that is 6 volt. You can have whatever you mind, you can get that. And now the time for calculating the RTH. So here just we have short circuit that particular terminal, because this consists of only independent sources. So we can have short circuit that particular voltage source, and here we can say that the 3 and 6 both are in parallel. So we can get the value of 3 into 6 upon 3 plus 6, that becomes 2 ohm. So we have calculated here, and we can have the equivalent. Here it is the equivalent circuit of that particular network. Here it is RL, so we can change the value of RL. Here it is 2 ohm, here it is 10 ohm. So it is 1.5 and 0.5, the value of IL. It is Thevenin equivalent circuit. Thevenin equivalent circuit. Okay. Now we'll do some more problem here it is the problem of AC circuit, that is most important. The concept is same, only different is that there is a calculation, somewhat complex calculations are there. We need to be very careful here. So here it is voltage source that is given 10 angle 0. Here it is the symbol of, it is the symbol of AC voltage source. AC voltage source. It is a symbol of AC voltage source. Just keep in mind. So here it is 10 angle 0. In AC system, we all know that the magnitude as well as their phase angle are there. Okay, and here we deal with the impedance that have a we already know that Z equal to R plus JX. That okay. So R is the resistance, X is the impedance. It may be R plus minus JX. Okay. So here it is 8 ohm. Here it is the symbol. The symbol is, it is inductor. Inductance. It is inductance. 8 ohm inductance means it is J8. JX hota hai. It is 6 ohm, that is capacitance. So minus J6. You can write it minus J6. Okay. And here the load is RL is 2 ohm. Okay. So first we have to find out the whatever you choose to find first. Okay, let find out the ZTH. Okay, so in case of this is independent source, so find out ZTH. Here it is ZTH, yeah, ZAB. Okay, so here it is short circuited. The voltage source is short circuited. The procedure is same for the DC as well as for AC. There is no change. So here it is J8 minus J6. Okay, I just correct them. So what is ZTH? ZTH, that is both are connected in parallel. Okay, so J8 into minus J6 divided by J8 minus J6. So J square minus J square, that becomes plus 8 into 6, 48 plus 48 divided by J8 minus J6. So it becomes J2. 1 upon J, that becomes minus J. Minus J 24. Minus J 24. Is it correct? Okay, I hope so. Here it is. 24 angle minus 90. Or you can write minus J 24 ohm. Minus J means angle 90, plus J means angle 90. We have calculated the value of ZTF. Okay. Now it's time to calculate the value of VOC. Okay. So here it is. The same thing is there. We can have the voltage divider rule in this case also. Okay. J8 minus J6. So total voltage given, that is 10 angle 0. We have to find out the voltage across this terminal. Let it be CD. VAB, that is equal to VCD. There is no resistance or impedance are there between AC and BD. Okay. So value of VAB, that is equal to VCD, that is your VOC. Okay. So what is the VOC? VOC, that is the voltage across this minus J6 ohm. Okay. So what is the total voltage? 10 angle 0 and minus J6. Okay, divide by J8 minus J6. Okay, so it becomes 10 into 6, 60 minus J60 minus J divided by J2. J cancel. Okay, so it becomes minus 30. Minus 30, it means the magnitude, because it consists of phase. So you can write it in a good way, that is 30 angle 180. You can not write minus 30 volt. It is not the case of DC, it is the AC. So we have to follow the system like R angle phi. Okay, R is your magnitude. Magnitude must be that is positive, and angle we can change that to 0. If it is minus 30, angle 0 actually. So we can have angle 0 minus replace. We have to replace the minus. Then we have to change the angle 130. So here we have calculated the VTS. Okay. So now we have so equivalent circuits are there that you can write it VTH, and here it is ZTH, and here your RL. So you can find out I VTH upon ZTH plus RL. Okay. Now it's over.